Thursdays, and then the homework that's due, what did I make it, 11 o'clock tonight? 11:55, do it for 11, okay? I'll post the solutions, so I can have Moodle do it, then we'll just post at midnight. I will not, just make sure it's very clear, because the solutions we posted, take any late homework, do not send it to me at 12:04, it will not be accepted today, okay? So make sure you get it in, have it due by 11, because I just won't take any late homework, because the solution's there, okay? Does that make sense? All right. Yes?
How many questions for the exam? Yeah, I know
No idea.
No idea.
No idea.
Okay, great. Thanks.
I should know by now, but I don't. Imagine something like 3 or 4 with lots of parts. Okay?
Are we supposed to be able to finish it during the hour and 15 minutes? Or if I don't, should I panic or?
So didn't you ask me this question once already?
Probably, I don't remember.
So I make it so that I can hit the calculator buttons, use my ruler, write as fast as I can in about 15 to 20 minutes. Now, that takes away all thinking and uncertainty, I know that. But that leaves you about 50 minutes for thinking and uncertainty.
Okay.
Is that enough? I don't know. It really depends. My goal is to have, say, 20 of you finish before the time's done. I don't know who those 20 people are. No, and they don't always do better. I've watched. A lot of times the people who do the best are people who sit and think and check. That doesn't mean you need to. I don't know why people leave early. I don't judge you if you do or you don't. I just know it's at the bottom of the pile. Okay, that's all I know. Okay? They don't always do the best. They often do a little better than average, but they don't often get the highest scores. The highest scores are usually the people who are meticulous. But I'm not, again, I'm not judging. I'm not looking. It's just, I can tell when you hand it in by this, where you are on the stack.
So you need a ruler?
And I was just about to get to that. You need a ruler and a calculator. Okay? The question that I always get, there is, I try, now I only have one TA because Suhasini, who's in Stony Brook, can't help me grade exams. It's just not going to happen, okay? So I have one TA to help me grade 89 exams. I try to have what I call no double jeopardy, meaning that if I have a problem that has multiple parts, that if you get part A wrong, and then you legitimately use the answer from part A for part B, and you get an answer that at least makes sense, and you did it correctly, you get full points, okay? So that it's like an independent problem. However, if you get that the purity is negative, and you don't, it doesn't trigger you to go, wait, my answer part A is so wrong, the B is wrong too, then I'll dock, because you need to understand that you can't get a negative answer, right? That means you don't understand B either. Does that make sense? Yeah.
Can you write a little explanation saying, like, I know my part A is wrong, but I did this part right?
Yeah. Oh, now, here's the thing with that, okay? Don't expect that that's going to automatically give you a better grade, but it does sometimes, okay? So my hint with that is, there are some people, and this happens, I've had like 5 or 6 out of 10 years of teaching, 11 years of teaching, where someone spent their whole time writing those, and they got like a 15 out of 100, okay? Because they just spent their whole time writing explanations. Don't do that, please. Okay? However, every once in a while I do give someone, oh, that explanation means, you get it, you get the thing that I'm looking for. Oh, maybe you get 3 points out of 5. And that 3 out of 5, that's worth it for writing a little explanation. But don't get carried away. Does that help? Please don't get carried away. Okay? But explaining that you know it is helpful. Or, I know this answer is wrong, it should be somewhere around 20%, and I got 35%. It should be 20% because of this. It's that because of that gets you the points. That you get it, that you got something. Does that make sense? But not always, so I'm not promising. So what I'm saying is I could just as easily just go, yeah, you wrote something, but all you did was redefine the problem, which happens a lot, okay? So my point is, do or don't, but always be careful, because sometimes that takes a lot of time. It's not always worth the investment, but at the same time, if you're stuck, it's not the worst solution to the problem, okay? There's a lot of test-taking strategies here, okay? I don't want that to be the effect here. At the same time, when I took this class, it was all take-home exams, or from Friday evening till Monday morning. And I would bet you guys don't want that compared to having an in-class 1-hour exam. I did. So I don't want to do that for multiple reasons, okay? Not just that it's a burden on you guys. Some of you probably wouldn't mind that, but most of you probably would. Especially if it's graded on a curve. Just think about it a little bit, why that's not such a good idea. Okay? So it means that your level of perfection has to be at a certain point, that you're not gonna you're not doing anything else for a whole weekend.
Probably not any more time than spend on homework.
What's that?
Probably not any more time than spend on homework.
Yeah, except that it's graded in a different way. It's graded on, is it right? Not, anyway, you don't want it graded with a different level of stringency, right? That's the exam. So, I know there's an element of raceness to this. I don't, race meaning it's going really fast. I really don't want that, but there's a lot of material. We've covered a lot of material, and I need to test it. And I don't want to race. It's not how fast can you go, but, you know, to some extent, I figure if you're going really slow, it's because you're reading the book and trying to learn it. You know, that's the kind of the nature of it. It's an open book exam. If I give you 4 hours, you should all get. I'm giving you the book and all your notes, right? If you come to class and you have the book, you should be able to do okay. You know, that's where it's coming from. So, but you know, if you've done the homework, it shouldn't be. You shouldn't have to go crazy fast. You just be able to be like, okay, go, you know, go right reasonable pace. Bring a ruler. Why am I saying this? If you haven't hit, okay, star. I know I've said this 3 times already. If you haven't practiced doing Cape Dealies with a ruler, do it. Because there's a couple of little tricks that you haven't thought about yet. I know that sounds dumb, but you have to know how to convert a slope into a line and a line into a slope. Otherwise, you can't figure out how many stages there are. Okay? Just, okay, I'm not going to take it away. It sounds silly. You all do it on computers. Practice it with a ruler. Okay? That's only going to be one little part of the problem.
Are we exclusively in this room, or is there like an overflow room?
Unfortunately, we are in this room. I can get double rooms if I do them at night, but then doing them at night is just, you probably saw how much it takes a bit of organizing. I'm guessing that Danhauer's evening exams probably work out fine, but anyway, it can be tricky. And then we have to coordinate. There was a lot of coordinating at the beginning of the semester between all the different classes you have. And this is just easier for me. So hopefully it's a little easier for you. 2 hours is probably more reasonable, but yeah.
We're all done here like 10 minutes earlier when we start.
No, because I can't, not everybody's even here that I could announce it.
That's against the rules.
I mean, it's a fine request, I just can't do it, because what if one person misses it? It's not fair. So, you know, and you know that there are people who only come during the exams. I don't know why, they never do well, but there are people, look around. This room was full on the first day. Where are those people? I don't know. They usually don't do well in the class, but it's not fair for me to do anything that's like purposely make it worse for them. Yeah.
Should we expect anything other than constant molar overflow for most of the problems?
That's a very good question. In that you understand what that question means, you're okay. Okay? But I think that for the most part, that's a reasonable assumption. But don't, if you go, oh, it means they're all easy, then you're probably like missing something. However, if you think, oh, that means that we're assuming that the average heat of vaporization between the 2 components is the same, if that's your response to, oh, we can assume constant overflow, you're doing all right. Do you see the difference?
Should we just take the average of the 2 if we're given them, or?
Well, remember, most of the time it cancels out.
Okay.
Remember, it makes it so that your operating lines are straight lines, which is, you know, it's a downstream effect. But yes, it's a reasonable thing for most of the problems. Notice that when we did Flash, we didn't assume CMO, but there's no CMO in Flash. Yeah.
If we're doing, can we expect like maybe non-quantitative problems on stuff like constant molar overflow and impacts back in?
Well, most of the problems are quantitative. Quantitative in that if you know, a ruler and a pencil is still quantitative. Okay, there's not going to be essay problems. Okay, there may be a why is this problem, but it'll be short. Okay, don't expect to write a page in a book. I'll expect a few sentences here and there. It's a grading and time thing. If you have to write a page in the book, that's half the exam. And anyway, so I don't know. Yeah.
As far as chapter 4 goes, are we doing chapter 4 all the way up to 4.4?
The hint always is there are parts in all the chapters that I didn't talk about in lecture. Okay? What I focused on in lecture should tell you what I thought was important. So you should know the book, but the parts that I didn't talk about, I'm probably not going to put on the exam.
Okay.
Okay? You you can judge that for yourself. That's probably true for most classes, except for people who tell you, make sure you read this part. I'm not going to lecture on it. Okay? But for the most part, that's how most faculty do. Okay? Yeah.
Quantitative or qualitative costing?
My hint for that is it's an hour and a quarter. And just, you have to figure that out later on, okay? If you did a full costing, it would take more than an hour and a quarter for one problem. That doesn't mean it's completely fair game. The whole thing's fair game. Just, does that make sense? And it's open book. Okay? But so if you've done that homework and you kind of worked through the problems, you're in good shape. Does that help a little bit?
Yeah, thank you.
So don't expect, you don't have to cost out the whole costing study. Okay? I think that's pretty obvious. Hopefully that's obvious.
That's a lot of typing into a calculator.
Yeah, no, there will be typing into a calculator. This is quantitative. So there is going to be calculation. Make sure you have a calculator, because doing this by hand is deadly. Okay, but I've watched someone try to do it, and anyways, let's just not go there.
He died.
Smoke came out of his mouth. I saw long division once on the side of it. That's just, it's as if twice to that person did not do well on that exam. I don't know what I was going to say about that. Like, the costing is, all the parts are fair game, but it's probably going to be a part, right? Just connect the dots, right? Does that make sense?
Yeah.
But the whole thing's fair game. Does that help a little bit? Not probably doesn't change much, but okay. Is that what you were expecting? Anyway, hopefully it's what you expect. My only hint is my style. I like to ask things you haven't seen before. But in that, you know this part, oh, I didn't know you could put those two together. Okay? So just be aware of that. That means it may be very simple, but it's something that hopefully will make you think a little bit. Okay? That's the exam kind of problem that I like. Ones that makes you have to think. And do you understand the thermodynamics? Not how fast can you calculate. Now, of course, you have to calculate. So speed helps a little because you have more time to think, but it's not the goal. Shoot.
How would you suggest studying for problems you've never seen?
Make sure you've done the homework and you understand the underlying principles.
What I've seen.
And did you get it? When you looked at the solutions? Not when a friend showed you and you go, okay, that makes sense to me. You did it yourself and you're like, this was hard. Oh, but I get it now. And I got the solution right. If you're there, and you understood all the lectures, and you came to all the lectures, and they all kind of sunk in, you're probably doing okay. The trick, and if you don't, if you want to do more, I only assigned 3 or 4 problems out of the book. There's a lot of good problems in there that I didn't assign. Go and do a couple more problems in the book. By yourself. I say by yourself because you want to make sure that you're not falling on that same crutch, that same friend, for that same part of that same problem. Make sure you can do it all yourself. If you want to know how to study. If you're really worried, if you're worried about it. But what usually happens is usually the people who are like fastidious studiers going through that, and they didn't need to in the first place, and the ones who think, anyway, you know how it goes. Okay? But so if you want, practice is the best way, there's no memorization, you have an open book, okay? Just make sure you understand it. It's open book, so you could learn it, that's why it can't be 4 hours, right? The point is, you know it well enough, you're like, oh, this is that equation, boom, you do this. Oh wait, I don't know how to, I can figure out how to do that, I know how this relates to that. Usually we go this way, it goes that way this time. Does that make sense?
Now up is down.
What's that? Yeah, something like that, but not quite. Okay? All right. I know exams are always stressful, but okay. Try to minimize it if you can. Everybody okay? Questions? All right. So I'm going to start a new topic, and so there's a couple comments. So this is okay. Homogeneous, azeotropic situation. So over the years, I've added more and more topics to this course. The course always had this, partly because I inherited it, not directly, but I had it from Phil Westmoreland, who taught it for a couple of years, and before that, Mike Malone actually taught this course, the author of the book. And so I inherited their slides, and actually, this course was a course way before that book was written, actually. He taught it before the book was published. And so this has always been in there. But As I've added more things like chromatography and crystallization and other parts that didn't used to be in this, used to be all distillation, I've tried really hard to maintain this homogeneous azeotropic for a couple of reasons. One, it's not taught in many schools, which might go, well, does that make it useful? I think it is, because azeotropes are very important for lots of current compounds. Second, I like the way this is developed, the way the book talks about this. If those of you who've spent time reading the book know that it's well written. And this is a topic that we're actually getting it right from the people who've kind of developed some of these theories and are used in industry. And the other thing is, this is kind of strange, but I actually think this topic's kind of fun and interesting. I didn't have it as an undergrad, and I really like it. And I hope you do too. It has a really long name that sounds really esoteric, homogeneous azeotropic distillation. And I'll explain what that means in about 10 seconds. And the other thing I want to say is, in order to get to it, I have to go, it's not very complicated actually, but it's going to be different from what you've seen before. So it has kind of an esoteric derivation. It's not really a derivation because it's not mathematical. But the getting into it takes a little bit of bending your mind around something you haven't seen before. But once you get there, there's a whole element of this which is kind of interesting. There are some neat puzzles that come out of this, and something that you haven't seen before. Okay, so we talked about azeotropes. We had this one azeotrope problem that you had previously in homework. Do you remember the pressure swing problem from chapter 3, right? Where you could get past an azeotrope by shifting the pressure. Do you remember that problem? And it moved the location of the azeotropes. It could produce an azeotrope in a low pressure column, then take that as a feed to a high pressure column, and then you'd be able to produce the other pure component. Do you remember that? Well, it turns out that most binary pairs move with pressure. Most binary pairs, water and ethyl is a great example. The azeotrope doesn't move with pressure. It moves with only a few select species. And when it does, of course, it's a very useful technique. But what do you do when it doesn't? Okay? So when pressure swing is not available, what we're going to do is we're going to add a third component. And that third component has a name. It's called an entrainer. Okay? There are 4 categories of entrainers. I'm going to describe 2. This whole section is just on the first kind. There are homogeneous entrainers. Oops. And they do not induce liquid phase separation. In other words, this is still a VLE. Okay? Then we have heterogeneous entrainers, which induce phase separation, liquid phase separation. And these are VLLE problems. So we have 3 phases, a vapor phase, a liquid phase, and a second liquid phase. Then we have entrainers, reacting entrainers. The reactive one of the species. And 4 entrainers that ionically dissociate. So, chapter 10 in the book, which I'm not going to cover in this course, talks about reactive distillation, and ionically dissociating entrainers is beyond the scope of this course. Okay, so we're going to look at 1 and 2. I'm going to spend the majority of the time on number 1. So, homogeneous entrainers. Okay, first of all, let me talk about what an azeotrope is. So at the moment, you think of it as where you have an equal composition between multiple phases. And you can see that in a VLE, maybe a binary VLE, that holds, and it's actually true. I can't think of any counterexamples in a binary VLE. But when we start adding third components or third phases, how do you say what's equal composition across all phases? Doesn't really work anymore. So an azeotrope is a state in which mass transfer occurs between phases but the composition of the phases remains constant. In other words, they're at equilibrium, and the compositions don't change. Okay? So this means that, this basically explains why isotropes are places where you get stuck. It's because you can't do further separation because of the compositions don't change. Okay. So now I have to go into the derivation of residue curves, so we can start talking about what we're going to do, how we're going to pick entrainers, how we're going to design extractive distillation, which uses entrainers in order to get past azeotrophs. Okay, so the whole point here is talk about ethanol water. There are two entrainers we're going to talk about a lot: ethanol water. Ethylene glycol is a homogeneous entrainer, and benzene is a heterogeneous entrainer. And we'll get to that. I'll explain how the benzene entrainer works when we get to heterogeneous. So, because benzene and water obviously form two phases, right? One in water, whereas ethylene glycol is completely miscible with both water and ethanol. Okay. So, but how do we design a system so that we can add ethylene glycol and get pure ethanol out? How does that work? In order to do that, I have to show you, we have to talk about something called residue curves. Okay, and this is going to be based on something called simple distillation. So in the simplest sense, and I don't know if you noticed this, but if you think about distillation from a historical standpoint, think about alchemy. Like, we jumped right from flash tanks to a really complicated distillation column pretty fast, right? That had a condenser on the top and a reboiler on the bottom, and had lots of stages. We just jumped right to that from flash. If you think about it, they started doing distillation with very simple things. They would put this thing's called a still. They put a mixture in that had some liquid volume, in this case moles of H. You'd heat it, heat Q, and what would happen is you'd get a vapor that would come off that you'd condense. We're not even going to worry about condensing it. And its composition of the vapor would change as a function of time. And if you measured the composition of the liquid phase, it would also change as a function of time. So here, H is the moles in the still. V is the vapor flow rate. Y is the vapor composition. And X is the liquid composition. Okay? So, what's the rate of change? Oops. We're adding heat to this, so don't worry about how much heat we're adding. Just a constant amount of heat. The rate of change of the number of moles in still is equal to, everybody see it simply? It's actually quite an easy answer if you think about 10 seconds. Maybe more than that. Rate of change of moles in the still is given by F.
The change in the vapor flowing out.
Is equal to V. Minus V. Okay, that's the idea. Okay? And if we had a species I, rate of change of species I in the still is given by, the same way, slightly more complicated. Yeah,
It's multiplied by the vapor.
yeah, minus VI, okay? So you can actually mix these two together. This is the product rule, right? So we have, these are both changing in time. The amount of moles in the still and the composition of X in the liquid phase is changing as a function of time. So you can't, none of those is a constant, but it's the product rule. And again, I'm going to say this one more time in a slightly different language. Bear with me. This derivation leads to these residue curves, which I'm going to build, simplify the analysis of azeotropic situations, okay? Rather than making them more complicated. I just have to go through this derivation in order to get there. Okay? So let's apply the product rule to the left-hand side there. You get that H dxi dt plus the 8xi dh dt, which is just minus v, is equal to minus v yi. Because v is just dh dt. Okay? We can rearrange this, and we get that the change in the liquid phase composition is equal to v over h xi minus yi. That's equation A. Okay? Well, we don't really care what size our still is. We don't care about h. We don't care about v. We want to just do this in a generic way. We want to think about how the change in the composition of the liquid phase depends on the difference in the composition between the liquid and vapor phase. We're not really worried about the rates or how much is there, because then it's very, what's the size of our container? We're not interested in that. So we're interested only in x's and i's, and how they depend on time. So, to adjust that, I'm going to introduce something that seems, again, esoteric, but all it does is it just makes it simpler. And I know oftentimes we do this and it makes it seem harder because now I'm going to add a new term that is really hard to understand, but once you get used to it, it really does make it easier. Okay? So I'm going to define something called warp time. And warp time is just xi is equal to v over h dt. It's just going to allow me to get rid of this v over h term. So now we can rewrite this term as the change in liquid composition. Let me make sure it's an x. With time, with warped time, is equal to the liquid composition minus the vapor composition. Okay, how is that useful? First of all, what's I? So if we want to understand what this thing is, it's not very hard. And also, it won't come up again. It's a little bit like how lambda cancels out everywhere. We're never going to see xi again. You just need to understand that all we're doing is changing time. So we can say that xi, which is a function of t, is just equal to the natural log of the initial volume in the still in moles over the change. The number of moles is a function of time. So it's just a function of the volume in the still. All it is just saying, how does that volume change over time? And because you're now divided by h naught, it's a little bit like non-dimensionalization. It just says it doesn't matter what size still we're working at. Okay, so if we want to understand how to use this, let's look at a binary mixture to start with. Obviously, in trainers, we can't do binary, can we? We have to at least do ternary. But for for now, let's do binary just so that we can work with something that we can handle. We can do the math on the board, okay? Let's start with constant relative volatility. So can we write it's just this. Can we take the derivative of that? Sure we can. It says that dx dxi is just equal to x minus y minus alpha x over 1 plus alpha minus 1 x. So it just says how the liquid composition is going to change. Sorry, I don't need a vector form for this. As a function of warp time. We could integrate that equation. And we get that xi is equal to 1 over alpha minus 1 natural log x naught 1 minus x over x 1 minus x naught plus natural log 1 minus x over 1 minus x naught. Okay. Now we plot that. No, I need more space. I'll write that again when I finish. If x naught is equal to 0.5, so the mixture, binary mixture, I'm going to put an equimole mixture in here like this. Okay? And if I plot that equation, it looks like this. It's asymptotic to 0. Okay. Lots of stuff. What does that mean? In the past, I've asked people to tell me how to what that should look like. But if you plot that equation, you get that. I'm going to do this the other way around. Rather than having you tell me what the curve looks like, I want you to tell me what that means. This is, what's x? I'll give you some hints. Liquid phase composition is a function of warped time in a simple still. Starting with a equimolar composition, what's x? Just to get you on the right track, there's a part that I'm missing out here. What's x in this equation, in the constant relative volatility model? What's that? It's the mole of, the liquid, but of what? Say it out loud. The lighter component. Now, that's the hint. What does that mean? Go ahead.
Well, it's kind of similar to the distillation column. As you get to smaller and smaller purity, it gets harder, so it takes more time.
You're looking at the secondary effect, and you're right. Before you get there, just tell me basically what's happening here. The most
So
simplest.
basically, the lighter component is going to disappear really fast at first from the system liquid, and then.
So what's happening to the liquid composition over time? What's that?
It decreases.
Just say it more clearly. You're right. What's the liquid composition of the what's this decreasing?
Lighter.
The light component. So that what's remaining in the still is getting what? If x is going down, what is the still being made up more and more of over time? What's that?
The heavy component.
The heavy component. And as you go to really long times, what's in the still? What's that?
Just the heavy component.
Just the heavy component. Does that match your intuition? Does that make sense? Does that make sense? So in a simple still, put heat in, the light component is going to come off first, going to come off fast. The amount that's going to come off is going to slow down, obviously. But at some point, what's left in the still is all heavy component. Now, how much of you have, that's a whole other thing, but that's what work time is getting rid of. We don't care about how many moles we have. What's empty composition is a function of time. It's becoming more and more heavy component. Does that make sense? Notice that it reduced to something that hopefully should be very intuitive, right? Or close to, okay? We can do the same thing with the empirical equation here. I'm not going to write the solution, but you can do the same thing with this equation. And if you choose your A and D correctly, you can have this model an azeotrope. Okay, remember that from binary distillation? You could use this to model an azeotrope. In other words, your x minus y, this equation will look like that. Okay, do you remember that? You can make that equation fit that. It's entirely empirical. We can then take the derivative. Remember, we can put x, put this in for y, and then we can integrate. What do you think it looks like? Do you mind if I just erase the curve out here and reuse it? Do you mind redrawing it? Okay. So, this time, oh wait, let me do one more thing. Let me go back. Just hold that for a second. I missed a thought. Okay, and I want this thought's a little more simplistic than this. So just hold this for a second. Okay, let's come back to the constant relative volatility model. Okay, I just want to explore a little bit what happens as I change the input. Okay, the 50-50, that kind of makes sense. What do you think happens if I increase the composition? What happens with warp time if I increase the amount of light component I put into the still at early times? I mean, at initial times. What do you think happens in this still? I put in 75%. It's an obvious answer. Someone tell me. Yeah.
Like component would drop to 0?
Yeah, it does the same thing. Okay. But then what happens if it's very, very close to 1? What happens if it's 0.99? Yeah?
It might take a little bit longer to drop to 0.
Sure. Okay. All still just plotting that and adjusting x naught. Okay. All we're doing is changing x naught. And you'll find you get this plot. This hopefully isn't surprising if everybody's paying attention. Let's now put in 1. Let's put in x naught is equal to 1. What happens in that still? Yeah?
It stays at 1.
It stays at 1. So what does everything do up until 1 with warp time? Yeah?
Drop all the way to 0.
It goes to 0 regardless of what x0 is until, and what is it when x0 is equal to 1? What do we have? Just simply.
Just the light component.
It's the pure, no, it's the, yes, it's the pure light component, correct. Pure light component. So we can describe this, instead of in 2 dimensions, we can actually describe this in 1. We can take out xi entirely. I told you it would be removed. And we can use this to say, that we have what's called a residue curve. This is the simplest one. That goes from an unstable node to a stable node. That's the simplest residue curve you're ever going to see. Do you see why one's unstable and one's stable? No matter where you start on here, where do you end up? You end up at the stable node. It's kind of like is not really an attractor, but basically what's happening is no matter what you do, you're going to end up there in a simple still. Right? You believe that, right? You make a still with any mixture, you're going to end up with pure light component. So pure heavy component. So the heavy component is a stable node, the light component is an unstable node. One last thing before I go to that next thought. What happens to temperature? From here to here. What's the temperature of the unstable node? Remember, this is still. Okay, this is a VLE. They each have equilibrium temperatures. Okay? What's happening as we go in this direction? Yeah, go ahead. Temperature increases. Okay? Does that make sense? That I can take all of what I just talked to you about simple stills and reduce it to a single line? This is representational, okay? It's almost qualitative, but basically it says, if we have a simple still, we're going to end up all with a heavy component. Everybody okay with that? Yeah? Now you're like, okay, what's it going to do with that? Well, this is where it gets interesting, okay? Let's put the azeotrope into here again, okay? So I can even give you a mixture that does this. We could do pentane dichloromethane. Again, you have a lot of intuition about that mixture. Okay. And we know that the binary looks a little bit like that. The values that we put in here is A is 4.2, B is negative 1.2. Okay, and it has an azeotrope. X azeotrope is equal to 0.52. The nice thing about this one, just for drawing purposes, is its azeotrope's about 50-50, close. Okay? What do you think if we now integrate? Now you could solve this entirely. That integration is actually the equation, the integral of that is in the book. You can type it into Excel or MathCAD or MATLAB, whatever your favorite program is, and these curves will come out. Okay? But I think that you could guess what they're going to look like. I'll just erase it and just draw another one. Liquid composition, warped time, 0, 1, 0, 1. Okay, in the simplest case, and that's a little above half, but anyway, let's make X naught here. What do you think that looks like? So this is dichloromethane's, so I think pentane's my light. So dichloromethane is the heavy. So if we have, say, 30% pentane, what happens in this system as a function of time? Go ahead, just say.
Just gonna look like the previous one.
Just going right before. Okay. Oops. Doesn't come back up. It's just okay. Now, think a little bit about azeotropes. What happens if I put in 75%? More dichloromethane. What happens in this case? What do you think happens here? Yeah, go ahead.
Asymptotically approaching 0.52.
It's gonna, no, yeah,
It's gonna go up.
it's gonna go up. It asymptotically approaches the dichloromethane. Similarly, if I get close, what's this one going to do? Underneath the azeotrope, it's going gonna go down. And the one just above it, it's gonna go where? It's gonna go up. And like before, if we go right near the azeotrope, just above or just below, what do you think that looks like? Do you think it changes anything? It just is, someone said it astutely over here. What's the effect on with warped time? It just goes, someone had shouted it out, but even it just goes slower, okay? So it takes more warp time. Just gonna see this continue to go towards pentane and dichloromethane. Does that make sense? You put it in a still. Remember, this is in a simple still. I'm gonna mix pentane and dichloromethane.